So, remember that section that we did in Chapter 7 that was just called Strategy for Integration? And it didn't really have anything in it. It was just, like, here's a bunch of examples. Yeah, this is another one of those. So this is called Strategy for Testing Series. And just as before, I think that's a weird name because if someone were to ask me, like, what's the strategy for determining whether a series is convergent or divergent, I would tell them, well, that depends on the series. That's really, there's no one answer to that. Okay? Similar thing here. So in other words, I'm just gonna do a bunch of examples today. If you read through the section in the book, 11.7, you're going to find that it's similar to the section called Strategy for Integration in that it doesn't really have a lot in it. It's just, yeah, good luck. So, yeah, we'll just do some examples today. All right, so I'm going to determine whether the series sum from n equals 1 to infinity of n minus 1 over n squared plus 1 is convergent or divergent. I did get that right, didn't I? Yeah, seems so. And by the way, I just want to point out, for most of the examples that I'm going to do today, there's going to be more than one correct method of doing it, but I'm just going to display one. So, if you want to determine whether this is convergent or divergent, well, the first thing I think to myself is, if this negative 1 here, and if this positive 1 weren't here, then it would be easier to deal with, right? So let's see if we can just get rid of those. So n minus 1 over n squared plus 1. Whatever that is, it's definitely less than n over n squared plus 1. And in turn, that's definitely less than n over n squared. Okay? Now this, in fact, happens to be 1 over n. So, now if you look at the sum from n equals 1 to infinity of 1 over n, well, that's divergent. That's the harmonic series, right? So that means that the regular comparison test, which was what I was kind of trying to set up here, that's not going to work. Okay? It's not going to tell us anything. You just came up with a series with larger terms that's divergent. So what? That's easy. What would be more impressive is if you could come up with something that was convergent and larger. Also, I just realized I messed up the example here. This is actually not the example that I meant to display, but that's okay because we can still do it. So that's fine. We'll just do one extra example. If you want to do this one, it seems like the easiest way to do it would be by the limit comparison test with the harmonic series. Okay? The limit comparison test says if you take two series and you take the limit as n approaches infinity of the ratio of their terms, so this would be n minus 1 over n squared plus 1. If you take this and divide it by 1 over n, as long as this limit is positive and finite, the two series will have the same behavior. So this is the limit as n approaches infinity of, well, if you do the whole copy change flip thing, you get n squared minus n divided by n squared plus 1. So then as n approaches infinity, well, let's see here. If you were to divide top and bottom by n, what you get is the limit as, no, not by n, by n squared rather. Limit as n approaches infinity of 1 minus 1 over n divided by 1 plus 1 over n squared. As n approaches infinity, these two terms just approach 0, so this is actually 1. So then by the limit comparison test, this series has to have the same behavior as the harmonic series. So the sum from n equals 1 to infinity of n minus 1 over n squared plus 1 is divergent. Okay? Now, what I actually meant to write here was instead, same directions, but it was instead the sum from n equals 1 to infinity of n minus 1 over n cubed plus 1. So that's different, right? Okay, and then if you do the same kind of reasoning, you say n minus 1 over n cubed plus 1. That's going to be less than n over n cubed plus 1, which in turn is less than n over n cubed, and that's the same thing as 1 over n squared. All right, so then the sum from n equals 1 to infinity of 1 over n squared is a convergent p-series. Okay, and that's just because 2 is greater than 1. So, by the comparison test, the sum from n equals 1 to infinity of n minus 1 over n cubed plus 1 is convergent, because it's a series that has smaller terms than a series that we know is convergent. Okay? All right, so that was supposed to be one example. It became 2. That's fine. All right, let's do another example. Let's suppose now we're dealing with the sum from n equals 1 to infinity of negative 1 to the n. Let's see here, negative 1 to the n times n squared minus 1 over n squared plus 1. Well, this is an alternating series, but n squared minus 1 over n squared plus 1, that limit is not 0. So that means the alternating series test does not apply. On the other hand, the limit as n approaches infinity of n squared minus 1 over n squared plus 1, well, we know that that's 1, so therefore the limit as n approaches infinity of negative 1 to the n times n squared minus 1 over n squared plus 1 does not exist. And if it doesn't exist, then by the test for divergence, By the test for divergence, the sum from n equals 1 to infinity of negative 1 to the n squared minus 1 over n squared plus 1 is divergent. Because the test for divergence says that if it is a convergent series, then its terms have to approach 0. As it is, these terms do not approach 0, so it's not convergent. Let's see, next up we have n raised to the 2n divided by 1 plus n raised to the 3n. So, n raised to the 2n divided by n plus 1 raised to the 3n. Well, that's a pretty complicated function, actually, because it increases very quickly, right? Well, I shouldn't say it increases very quickly. I should say the numerator and the denominator individually, they increase very quickly. So like when n is 1, this becomes 1 to the 2. When n is 2, it's now 2 to the 4. When n is 3, it's now 3 to the 6, which is already pretty huge. By the time it gets to 5, by the time n gets to 5, it's going to be 5 to the 10, which is enormous. And the bottom is also growing very quickly too. When you see something like this, though, where top and bottom are both being raised to some exponent that's dependent on n, it would be a good idea to consider using the root test. So, let's see what happens if we do that. We want to take the limit as n approaches infinity of the nth root of the absolute value of an. Now in our case, that's going to be the limit as n approaches infinity of the nth root of, let's see here, n raised to the 2n divided by n plus 1 raised to the 3n. Now that happens to be the same thing as the limit as n approaches infinity of the nth root of n squared divided by n plus 1 cubed raised to the nth power. So then if you take the nth root of something raised to the nth power, well, that's just going to be, those two things are just going to cancel each other. So we'll just get the limit as n approaches infinity of n squared divided by n plus 1 cubed. And so now the easiest way to do this limit is to divide top and bottom by n squared. If you do so, then you'll find that this limit is 0, which I'm pretty sure is less than 1. So, by the root test, the series is convergent. Well, I guess I should say it's absolutely convergent, which therefore implies that it's convergent. All right, next up we have n to the 4th divided by 4 to the n. Okay, so n to the 4th divided by 4 to the nth. We're going to determine whether this is convergent or divergent. Easiest way to handle this one is by the ratio test. So this is going to be the limit as n approaches infinity of the absolute value of an plus 1 divided by an. In our case, that's going to be the limit as n approaches infinity of the absolute value of, let's see here, on top we're going to have n plus 1 to the fourth. On bottom we're going to have 4 to the n plus 1. So that's the numerator. And then in the denominator we're going to have an, which is just n to the fourth divided by 4 to the nth. This is the same thing as the limit as n approaches infinity of n plus 1 to the fourth divided by 4 to the n plus 1 multiplied by 4 to the n divided by n to the fourth. N copies of 4 on top, n plus 1 copies of 4 on bottom. And many of those factors will cancel. So what we're left with is just the limit as n approaches infinity of n plus 1 to the fourth divided by 4n to the fourth. This limit is 1/4. The easiest way to see that is by dividing top and bottom by n to the fourth. And of course, 1/4 is less than 1. Therefore, by the ratio test, the series is absolutely convergent, which makes it convergent. Let's see, next up we have 1 over k times the square root of k squared plus 1. So, the sum from k equals 1 to infinity of 1 divided by k times the square root of k squared plus 1. So let's note that if you were to delete that 1 under the square roots, then what we get here is, let's see, 1 over k square root of k squared plus 1. If you delete that 1, then what we'll get is 1 over k times the square root of k squared. Square root of k squared is just the absolute value of k, and since k is non-negative in this case, that means that this is just going to be k times k, which is k squared. Now this denominator is smaller than this denominator, which means that this is a larger fraction. Now then, sum from, no, not n, but rather k. Sum from k equals 1 to infinity of 1 over k squared is a convergent p-series. So, by the comparison test, the sum from k equals 1 to infinity of 1 over k times the square root of k squared plus 1 is convergent. Next up we have the sine of 2n divided by 1 plus 2 to the n. Okay, so when I look at this series, I noticed that it's not alternating, but its terms are not all positive either. Sine of 2n, that's going to have some pretty erratic signs, okay? SIGNs. It could be positive or negative depending on what n is, right? And it's definitely not going to flip back and forth every single term. So this is weirder than an alternating series, so I prefer not to have to deal with that. And the best way to not have to deal with that is to take the absolute value. If you take the series of absolute values, what you'll be asking is whether the series is absolutely convergent or not. If that's true, we're done. If it's false, then we still need to check whether it's conditionally convergent. So we'll cross that bridge if and when we get to it. So let's consider the sum from n equals 1 to infinity of the absolute value of the sine of 2n divided by 1 plus 2 to the n. Well, this is the same thing as the sum from n equals 1 to infinity of the absolute value of the sine of 2n divided by 1 plus 2 to the n. Right, because 1 plus 2 to the n is positive, so we don't really need to worry about that part. Now, the absolute value of the sine of 2n, whatever that is, it's going to be less than or equal to 1. So this is definitely less than or equal to 1. And of course, then you just divide both sides by 1 plus 2 to the n, and since 1 plus 2 to the n is positive, there's no need to flip the inequality. Okay, so now we can just deal with this one. But this one is also a little bit annoying, right? Because it has that 1 in the denominator. Okay, well, if you delete that 1 in the denominator, you get 1 over 2 to the nth power. And that is the same thing as 1/2 raised to the nth power. Now let's think about that for a second. The sum from n equals 1 to infinity of 1/2 raised to the nth power. This is a convergent geometric series. Okay? And so by comparison, that means that, by the comparison test, I should say, the sum from n equals 1 to infinity of this smaller series, which is the absolute value of the sine of 2n over 1 plus 2 to the n, is convergent. This means that the original series, the sum from n equals 1 to infinity of the sine of 2n over 1 plus 2 to the n, is absolutely convergent. And if it's absolutely convergent, then it's also convergent. Okay? And this illustrates a main reason why we even defined absolute convergence to begin with. It's because it's not just this useless concept. Showing that something is absolutely convergent is a good strategy for showing that something is convergent. Okay? Sometimes, like in this case, for example. All right, now let's look at the square root of n to the 4th plus 1 over n cubed plus n. Let's see here. So we have the square root of n to the 4th plus 1 over n cubed plus n. We're going to determine whether that's convergent or divergent. So, the first thing that I think when I look at this is, if this 1 weren't here, then I could just take the square root of n to the 4th, and that's just n squared. So, let's see what happens if we do that. So, if we take the square root of n to the 4th plus 1, and divide that by n cubed plus n, well, that's equal to or not equal, but rather less than, it's less than the square root of n to the 4th divided by n cubed plus n. Now, wait a second. No, I got that wrong. Of course it's not less than, it's greater than. We're making the numerator smaller, so of course the new fraction should be smaller. Sorry about that. All right, so then you take the square root of n to the 4th, that's just n squared. So now we have n squared over n cubed plus n. You can now factor an n out of the denominator and cancel it with one of the factors of n on top. So then what we'll get here is n divided by n squared plus 1. So now if we can show that this is divergent, then by the comparison test, this will also be divergent. If it's convergent, well, we'll cross that bridge when we get to it. There are a couple of ways to show that this is divergent. One way is by the integral test. That's totally fine. Another, probably easier way is to compare it to the harmonic series with the limit comparison test. So the sum from n equals 1 to infinity of 1 over n, this is the harmonic series, and as we know, it's a divergent p-series. Now, if you take the limit as n approaches infinity of n over n squared plus 1 and divide it by 1 over n, so doing the limit comparison test here, this is the same thing as the limit as n approaches infinity of n squared divided by n squared plus 1. That happens to be 1. All right, so this indicates that the sum from n equals 1 to infinity of n squared over, n over n squared plus 1, that has to have the same behavior as the harmonic series, which means it's divergent. Okay, so this means that the sum from n equals 1 to infinity of n over n squared plus 1 is divergent. And now if that's divergent, and this thing has larger terms, then that means that this thing is also divergent. So by comparison, the sum from n equals 1 to infinity of the square root of n to the 4th plus 1 divided by n cubed plus n, this has to be divergent. Let's see. All right, next up is negative 1 to the n minus 1 over square root of n minus 1. So this is the sum from n equals 2 to infinity of negative 1 to the n minus 1 over the square root of n minus 1. Well, this is an alternating series, so I wonder if we can use the alternating series test on it. Well, the sequence of absolute values, usually call that Bn. In our case, that's going to be 1 over the square root of n minus 1. let's see here. If you take bn plus 1, well, that would be 1 over the square root of n plus 1 minus 1. Now, this denominator is larger than this denominator, which means that this whole fraction is smaller. This is what we mean by bn, and this is what we mean by bn plus 1. This shows that bn plus 1 is always less than bn, so it's a decreasing sequence. And of course, if it's decreasing, then it's also eventually decreasing. Also, if you take the limit as n approaches infinity of bn, well, that's the same thing as the limit as n approaches infinity of 1 over the square root of n minus 1. That denominator grows without bound, and so this is just going to approach 0. So, by the alternating series test, the series is convergent. Let's see. Next up we have the cube root of k minus 1 over k times the square root of k plus 1. So sum from k equals 1 to infinity. The cube root of k minus 1 over k times the square root of k squared plus 1. Did I get that right? I might not have gotten that right. I did not. In fact, this should be the square root of k plus 1. In parentheses, actually. So we should have square root of k plus 1. All right, that's more like it. Okay, now, again, you know, if those ones weren't there, this would be easier to deal with. So I wonder what happens if we just get rid of them. Let's see, so we have the cube root of k minus 1 divided by k times the square root of k plus 1. If you delete that 1 from the numerator, then you make the fraction smaller. So this is larger than the cube root of k divided by k times the square root of k plus 1. Wait, no. Of course you don't make the... Okay, so if you make the numerator larger, then the fraction will be larger. So this is what's going on. You add 1 to the numerator, of course that makes it larger. Yeah, sorry, I get this messed up for some reason a lot. All right, now, if you delete this 1 in the denominator, then you're making the denominator smaller, which would make the fraction larger. So this is actually smaller than the cube root of k divided by k times the square root of k. Now, this can be rewritten as k to the 1/3 divided by k to the 3/2, right? Because we have k to the 1 times k to the 1/2. You add the exponents, you get 1 plus 1/2, and that makes 3/2. So now let's see, we want to subtract these exponents, so let's see here. We have 3/2 minus 1/3. If you find a common denominator here, well, I guess the easiest would be 6. So this is the same thing as 9 over 6 minus 2 over 6, which makes 7 over 6. Okay, and so this ends up being 1 divided by k to the 7 over 6. So let's see here. The sum from k equals 1 to infinity of 1 over k to the 7 over 6. Well, that would be a convergent p-series, right? Because 7 over 6 is, of course, greater than 1. So this is a convergent p-series. And so by comparison, the original series converges. So by the comparison test, the sum from k equals 1 to infinity of the cube root of k minus 1 divided by k times the square root of k plus 1 is convergent. Let's see what we have next. Okay, so this is 1 over 2 plus the sine of k. So we're going to take 1 over 2 plus the sine of k, and we're going to try to determine whether that's convergent or divergent. Now, of course, the sine of k is always greater than or equal to -1 and less than or equal to 1. If you add 2 to everything here, then what you'll get is that 1 is less than or equal to 2 plus the sine of k, and that in turn is less than or equal to 3. All right. So then that means that, well, okay, so 2 plus the sine of k is less than or equal to 3. That means that 1 over 3 is less than or equal to 1 over 2 plus the sine of k. But let's look at the sum from k equals 1 to infinity of 1/3. Well, that's divergent, right? Okay, this is divergent because, of course, its terms don't approach 0, they just approach 1/3. So this is divergent by the test for divergence. Therefore, by comparison, this series with larger terms has to also diverge. So by the comparison test, the sum from k equals 1 to infinity of 1 over 2 plus the sine of k is also divergent. Okay, next up we have n times the sine of 1 over n. Well, that one's a little weird, right? This might look familiar to you from Calculus 1 because you took limits of functions like these as n approaches 0. But, and you did that using the squeeze theorem. But we don't want the limit of this thing as n approaches 0. We want to know whether the series converges or diverges. So if anything, we would be more interested in the limit as n approaches infinity. of n times the sine of 1 over n. If this is non-zero, then for sure this series diverges by the test for divergence. If it is 0, we'll cross that bridge if and when we get to it. Well, let's see here. As n approaches infinity, 1 over n approaches 0, and the sine of 0 is 0. N, meanwhile, is of course approaching infinity, which means that this is an indeterminate form of type infinity times 0. So, the easiest way to handle this is by using L'Hopital's rule. So we're going to have to set that up by turning this into a fraction first. We're going to say this is the sine of 1 over n divided by 1 over n. Now, L'Hopital's rule says that if, and I guess I should mention one more thing. So this is now an indeterminate form of type 0 over 0. So now L'Hopital's rule allows us to take the derivative of the top and the bottom individually. So this is the limit as n approaches infinity of, let's see here, according to the chain rule, the derivative of the top would be negative 1 over n squared times the cosine of 1 over n. All of this is divided by the derivative of 1 over n, which is negative 1 over n squared. So naturally, the negative 1 over n squareds cancel out. So what we get here is the limit as n approaches infinity of, sorry about that, the limit as n approaches infinity of cosine of 1 over n. Now as n approaches infinity, 1 over n approaches 0, so this approaches the cosine of 0, and that happens to be 1. Well, I'm pretty sure 1 is not 0. So by the test for divergence, the series is divergent. All right, now let's look at n squared plus 1 over 5 to the nth power. This one is another ratio test. So we're going to take a look at the limit as n approaches infinity of n plus 1 squared plus 1 divided by 5 to the n plus 1. All of this is divided by n squared plus 1 divided by 5 to the n. This is the same thing as the limit as n approaches infinity of n plus 1 squared plus 1 divided by 5 to the n plus 1 multiplied by 5 to the n divided by n squared plus 1. N factors of 5 cancel from top and bottom, so we're left with the limit as n approaches infinity of n plus 1 squared plus 1 divided by 5 n squared plus 5. And so now as n approaches infinity, this just approaches 1/5, which is less than 1. So by the ratio test, the series is absolutely convergent, which makes it convergent. There are two more examples in my notes, which I think I'll leave you to look at your leisure, because they're not that much more difficult than the ones that I've talked about today, and hopefully that will give you some idea of how to think about these problems. Not just to watch someone do them, but also to read a solution of them. Okay? So, homework is up. Go ahead and get some practice with this.